Hey, good afternoon, everyone. If you're on the East Coast, I suppose, and good morning, good evening, wherever you're dialing in from. Super nice to have you back. A week later, last week we had a great session on vLLM Omni. This week we'll be discussing the LLM compressor updates. There's a lot of good new stuff there. By the way, I'm Sasha. I realize that my name is not written down anymore now that we moved over to the Google suite for vLLM. But my name is Sasha, and I manage technical marketing over at Red Hat. I'm joined today by Michael Goin, who is a core maintainer of the vLLM project, also works at Red Hat, as well as Kyle Sayers and Charles Hernandez, who are on our model optimization team and quite experts. Any question that I have about compression or LLM compressor, I always go to Kyle and Charles. So you guys are in great hands today. Let me submit all these people. So do you want to go to the next slide, Michael, please? So as I said, today we'll talk about LLM compressor, and then we'll go back to our regular bi-weekly schedule. We'll be discussing the latest trends in AI agent applications coming up, and also vLLM on Intel CPUs. We do record all of these meetings. That actually reminds me that I should start recording. Sorry, guys, last minute. So we do record all of these meetings. We share them across social. They're also, you can find them on YouTube. We do have a playlist with all of the previous sessions. We link all the slides in the YouTube description, so you can also access the slides, talking about slides. Michael, did you put them? Perfect. Thanks for sharing it with everyone. Anyway, so with that said, I'm going to pass it over to Michael for a quick update. I don't think there was a release. Last week, actually, Michael covered 3 releases of vLLM, and we did post that video on our X account. Definitely check it out. It's 8 minutes worth watching. So I don't think we have a release now, but there are a few updates, and then we'll go over into the LLM compressor. So Michael, with that, I'll pass it to you.
Yeah, thanks, Sasha. Good to see everyone again. So we have just a few sort of community blogs and releases to talk about, model releases, that is. We're working on a big 0.20 release for the Torch 2.11 update and CUDA 13 update. Stay tuned for that. But to kick us off, let's introduce and make sure you know what vLLM is. It's the de facto standard for production large language model serving. It's the most popular open source project for that, with over 75,000 GitHub stars and a very active community where we land over 30 commits every day. It's deployed on millions of GPU hours every day. And has we have a vibrant Slack, which you're very much invited to, both for development and for questions. It's a very popular project with a lot of development, but it's also from a very wide group of companies, both in industry and academic institutions as well. Of course, originally started from UC Berkeley. It's grown to be used in production by Meta, Amazon, Mistral, LinkedIn, Microsoft, Google, so on and so forth. And we have thousands of contributors that have landed code in the project to this date. It's a Python-based library, so you can just pip install vLLM and then go ahead and immediately start serving your models from Hugging Face or from your local disk. Run those models, of which we support hundreds of different architectures, of course, on NVIDIA GPUs. With really great performance, but vLLM as a software library, of course, offers the abstraction of running them across, a dozen plus different hardware accelerators, even with CPU backends or Apple Metal backends now, and then running those models across more than one accelerator with many different types of parallelism, tensor, expert, data, context parallelism built natively into vLLM, and then even disaggregating different parts of the inference system, or really the LLM inference pipeline, like having separate vLLM instances for prefill and decode, transferring KV cache between them, or disaggregating encoders for multimodal models. Of course, especially today, I want to note how vLLM is more than just the vLLM project itself. It's an ecosystem of other projects, on the GitHub organization, and of course the larger open source AI ecosystem. LLM Compressor, which we'll talk about later today, with exciting developments, is a part of the vLLM project, but also vLLM Omni, Guide LLM Speculators, and so on and so forth. So yeah, it's a really active open source project, and we're really glad you're here to learn more ultimately. So I'll kick off on some of the blogs and notable posts I want to share. There was this great blog from some Hugging Face folks on how they built an efficient OCR pipeline that actually powers their papers every day service, which I actually rather like. It's a good way of figuring out between all the maybe hundreds of papers that get published every day in this space of AI, which ones are getting upvoted and have nice summaries and tags and things in a nice searchable database. Kind of like a more usable front end for archive. But they use vLLM running a Chandra OCR model very efficiently on some cheap L40 GPUs to ultimately power new capabilities that they built into their paper service. And they built that pipeline with Codex, which I thought was pretty cool, using a closed source model to make a more cost-efficient pipeline with open source tools and infrastructure. At least we know that ChatGPT knows how to use vLLM rather well. Check that blog out. It's a cool usage. I also want to shout out, we landed a spotlight blog on the vLLM Korea meetup, which is the second one in Korea. We had one last year with some great presence from really large enterprises, obviously Samsung, Naver Cloud, Rebellions, Upstage AI, and Squeezebits, and of course Red Hat ourselves. I just recommend reading through the blog and seeing all the things that were talked about in the presentations that were there. It was a really diverse meetup, and really happy about the growth in the community in South Korea there for vLLM and ultimately open source inference serving in production. Lastly, I can't help but comment on the very recent Qwen 3.6 release today, at least the first one of their open source releases for Qwen 3.6. This is for the sort of medium MOE, the 35 billion parameter replacement for the Qwen 3.5 size. This I think greatly improves performance, especially relative to the 27B dense Qwen 3.5 model that sort of got some hype as blowing the MOE out of the water. So I'm really glad to see that it's at least some proof that MOEs aren't a dead end and are actually still really useful and can go much farther and still be, of course, very much more efficient than dense models. Reminder: this is a model with only 3 billion active parameters per token, so much faster than a 27 billion parameter dense model. And of course, there's no architecture changes, so this runs in vLLM and plugs and play just like any Qwen 3.5 model. So thanks to the Qwen team for releasing it. That's all I have to cover today for vLLM. No release. We'll have one soon. And I'll hand it over to Kyle and Charles to talk about LLM Compressor.
Cool. Thanks, Michael. We'll give a quick introduction and we'll get into it. So I'm Kyle. I'm here presenting with my coworker, Charles. We're both on the model optimization team here at Red Hat, and we are core contributors to the LLM Compressor. LLM Compressor, if you're not familiar, is a library under the vLLM organization, which provides tools and a framework for optimizing large language models for deployment, typically using algorithms related to quantization. So we most recently had a release, our v0.10 release, and with it comes a lot of really great features that we're excited to share with you. We're going to talk about a few of them here. So the core ones being a refactor of our offloading and extended support for distributed model compression. Both of these being implemented with the ultimate goal of supporting very, very large models and compressing those with as minimal GPU hardware as you need. Cool, so we'll jump into it. So as I mentioned before, LLM Compressor is a framework and tool that allows you to implement algorithms for quantizing large language models and then deploying them on vLLM. We sit kind of in the middle between having a pre-trained or fine-tuned model and serving that on vLLM. So the workflow is essentially that you would take a large language model that you've fine-tuned or is a base model. You run it through LLM Compressor, which applies state-of-the-art algorithms in order to quantize that model. And then that quantized model is then saved in the compressed tensors format and is served directly on vLLM in a very native and integrated way. So LLM Compressor, unlike vLLM, faces kind of different challenges when it comes to the performance engineering of quantizing large language models. Typically, quantizing large language models requires some sort of level of calibration of the model in order to maximize the accuracy recovery of using those models. And typically, we use a technique called layer sequential calibration in order to perform this. vLLM typically kind of loads the entire model into some sort of VRAM memory, unless some sort of offloading is used. In LLM Compressor, we typically keep the model entirely offloaded and only onload the layers that we need when they're needed. And this basically allows us to compress extremely large models, like trillion parameter models, only using a single GPU or just a couple GPUs. So the flow basically looks like this. Typically, you have your large language model, and we split it up into kind of all of the decoder layers that make it up, right? Then we simply step through the model and run the entire data set through one of the layers, and then save all of the outputs of that layer, which then move on to the next layer. So we sequentially onload each of the layers one at a time. And by doing this, we maintain the same kind of throughput characteristics that you would expect, but not having all of the entire model parameters onloaded at the same time. So this is a really powerful technique. However, it requires some sort of implementation of offloading. Previously, we had relied on a library provided by Hugging Face called Accelerate in order to implement this offloading. This was a really great and powerful technique at the time because it integrated directly within Hugging Face transformers model definitions. But now, yeah, we basically found that it had kind of limitations when it came to being able to expand beyond its previous use case. So we basically found that it was much better to kind of rip out kind of what we had previously and implement our own native offloading implementations. This comes with a couple of benefits. One, this new implementation, sorry, I'm like very sick today. It's like allergy season. But this new implementation comes with a lot of benefits. So the first is that it's expressly built for the LLM compressor use case. This means things like adding new parameters, like quantization parameters, like scales. It also supports virtually all transformers model definitions in a way that the other Accelerate architecture didn't. It has better performance because we're only onloading the specific parameters that we need, rather than onloading all of the parameters associated with a module. And then finally, the most important part is that this new implementation supports distributed offloads, meaning that you're able to share a model offload across different processes that might be processing the model calibration in parallel. So the core abstraction that is at the key of the offloading implementation is the offload cache. And the offload cache is a abstract base class, which simply implements like a mapping between the name of a parameter and its offloaded value. So offloaded either to the CPU or disk, or GPU in some cases. And then simply all we have to do is subclass this offload cache in order to implement different kinds of offloads. So for example, CPU offloads, you implement an onload method, which tells you how to take a CPU tensor and move it onto the GPU, and then an offload method, which tells you how to take a onloaded value and then offload it into the CPU. And this abstraction that we found is to be very natural because it plugs directly into the module parameters and buffers members of Torch modules. So this makes it, yeah, this is just like a very natural abstraction, and it means that it's very extensible to different kinds of offloads. Currently, we support 5 different kinds of offloads. So we support offloading your model to disk. This is a zero copy technique, meaning that like if your model is like loaded on disk, we don't create another copy immediately until those parameters might be modified. So disk offloads, we support CPU offloads as we did previously, as well as GPU offloads. So if you want to keep your parameters on GPU memory for faster reads and writes, you can do that as well. The key one that we want to implement, and what is key to kind of implementing the distributed algorithms that Charles is going to talk about a little bit later, is supporting these types of offloads in distributed processes. So when it comes to like CPU offloading between multiple processes, we typically handle this using shared memory, which is often provided by most operating systems. And shared memory basically allows different processes to hold pointers to the same data. And yeah, this basically means that you can do asynchronous writes and reads to this data without requiring syncing or duplication of that CPU memory across the processes. Disk offload is also supported as well. This is obviously a little bit simpler, but same core idea, right? Where the disk is a shared device between all of the processes, and all of the processes can read and write asynchronously. GPU offloading is, yeah, the last one here. This is kind of similar to like what you might see with like an FSDP kind of situation, where you have some of the parameters being stored across multiple GPUs. And this has a benefit over CPU offloading because, you know, typically in most platform setups, you have like NVLinks and interconnects that make these GPU to GPU processes transfers much faster in terms of throughput. Cool. Yeah, so the implementation is on compressed tensors if you're interested in taking a look. The compressed tensors library kind of exposes these through the offloaded module context, which is a pretty easy plug and play into just loading your models. So your typical model from pre-trained loading function, you just call that within the offloaded model context, and the offloaded model context will intercept that load and replace all of the loads with loads into the compressed tensors offloading implementation. I'll also mention here that if you're doing something like a disk offload, you'll want to provide like an offload folder where new tensors can be written to. Cool. Yeah, and this also plugs in directly into distributed context, which Charles will talk more about how to utilize. But if you're in a distributed context where you've already initialized your distributed process group, offload model will detect that and automatically make sure that you're only loading the model once, and then any offloads that happen are being shared across all of the processes. Cool.
Right.
That was a quick. Yeah.
Please go,
Kyle.
Finish and pass it.
Cool. Yeah, that was a quick overview of the offloading implementation. There's obviously a lot of really cool abstractions and software there. So I encourage folks to take a look or reach out to me if they're more interested in contributing to something there. But yeah, as a kind of background, I'll hand off to Charles, who will talk more about the distributed algorithms that we've implemented and how they're benefiting large language model, like very large model optimization in LLM Compressor.
Since we have some time, guys, do you want to, and there are 2 questions, Kyle, in chat, one from Ryan and one from Mohammed. Do we want to quickly address those before we go to Charles?
Yeah, let's take some time here. So let's see. Ryan, you asked a question, is offloading only used when the model doesn't fit on GPU? Typically, we always offload the model. And this is just because not only for like standardization, but also, yeah, I mean, there are configurations that you can use in LLM Compressor to keep the model entirely onloaded for like very, very small models. But you also have to consider that, you know, your calibration data itself also typically needs to be offloaded, because the calibration data itself, like, you know, if you're calibrating with like 2K samples, or sorry, 512 samples, that can take up like 550 gigabytes on memory. So that's also a huge cost too. So some level of offloading is often required. But yeah, to answer your question, not necessarily, but typically, especially for larger models. Mohammed, you're asking, I have doubt on how does using compressed tensors offloading affect the ability for LLM Compressor to handle large workflows, especially when working with multiple systems or distributed? Yeah, I mean, if you want to kind of expand on what your doubt might be there, I can say that we've been using this offloading scheme for quite a while now and seen pretty close to linear speedups. So it definitely works, and definitely is correct in terms of being able to share the offload between processes. I can definitely talk more about like how the implementation works. Yeah, if anyone is interested or wants to ask a more specific question there.
Got it. Thanks, Kyle.
Cool.
All right.
All right, Charles, off to you.
Cool. So yeah, I will talk about DDP in version 10. One of the major reasons why we added all the offloading, like native offloading support, is to enable these DDP workflows. Trying to release models that were extremely large could take like, an entire day to apply quantization to. So doing something to speed it up was a necessity both for our team and usability of the platform. So okay, cool, it's working. So yeah, so sequential onloading and DDP have a couple differences from the sequential onloading without DDP. And to emphasize this, me and Kyle made sure not to coordinate when we created our diagrams for sequential offloading and calibration. So yeah, as you can see here, you have 2 GPUs and you have all these modules that are offloaded either to CPU or to disk. It doesn't change significantly. And then in a very normal fashion, you have to onload all the modules that you want to apply quantization to, or whichever part of the model you're in during the calibration. And then you run your activations through it that you stored from the previous chunk. And then from there, you normally do some amount of communication has to happen. And I'll go into a bit more specifics in a moment. And then after that, you apply a quantization and update the offload so that you record the actual quantization that you performed. So in this case, the quantization is the lines instead of the fully filled in background. So this might seem a little inefficient, right? Like GPU 1's not doing any communication here, and you've duplicated work by applying quantization on both GPUs simultaneously. You can do something more along the lines of this, where you assign which module goes, is quantized by which GPU, and then you update, and then you have to do broadcasting. And depending on the workflow, this will be more efficient. So concretely, like one example is GPDQ. This is, I think, the only one we actually finished in version 10, but the other ones have already been completed anyway. So for GPDQ, when I talked about that kind of weird communication step, what happens in the very start here, you do your calibration, your forward pass over that part of the model with your data, and then from there, you have accumulated some type of quantization statistic depending on the technique you're applying. In this case, it's a Hessian for GPDQ. And you need to, the data, like you have partitioned your data into two pieces, and that means that your Hessians need to be reduced before you can do any actual quantization. So there's a communication step that happens where you're combining your Hessians, and then from there, assuming you're doing a coordinated kind of implementation where each shard is taking some amount of the modules and applying quantization to it. You then apply quantization to the set of modules that you've been assigned, and then broadcast it back to the other one so that everyone's kind of on the same page. So in this case, we only really need one communication step before the quantization, and one after, just to keep everything up to date. But other implementations might require a bit more. So in this case, for auto round, which is accumulating a gradient that then needs to be reduced across the different ranks, you don't need to do another round of communication, because as you can see, once you have the orange gradients, the red and the yellow make the orange gradients, you apply quantization on all the ranks simultaneously, and each one is duplicating work, but that's faster than adding an additional communication step. So this one is a little bit maybe simpler because you only need to do one communication step, but you end up duplicating a bit more work. And so this is also available in I think main currently AutoRound. And then there's also the most recent one we worked on was AWQ, which is a bit more complicated. You have to do your initial communication step after you've accumulated your activation means for AWQ. And then once you have these accumulated, you then have to run through the data for a bunch of different potential quantization settings. And you're trying to find which one's the best one. And rather than doing a module parallel implementation, we have each of the ranks do all the math for all the modules with their set of the data. This way we don't have to like do any data coordination or anything like that. And then once the errors for each of these different options have been found, we reduce it again, and then do the kind of duplicated work quantization represented here with this like dotted line blue module that's taking into account the orange error values to do AWQ. So yeah, so this one is the most complicated, but it's ends up being a lot faster. Actually, I'm not talking about that yet. I'm talking about the actual changes. So in practice, the only thing you need to do, so there's a lot of text here, but the only real important part is whether you can see that you have to set up this init dist step. I think Kyle, you could see that on one of his slides as well. You have to have the sequential offloading context manager, set how you want it offloaded, which you can just do auto. And then you can optionally partition your data based on what rank you're on. That number 2.5 there is in orange is optional. You, in general, don't want to load, like if you have 8 GPUs, you don't want to, and then you're offloading to CPU, you don't want to load your data 8 times and then offload it to like CPU. That wouldn't be good. But you don't, if you have enough CPU memory or you're doing disk offloading, it's fine. And then lastly, you just have to set it off with torch run to set everything up. So there's only like 3 or 4 things you actually need to change to go from a normal implementation with of a LLM compressed model to doing it with DDP alongside getting the hardware. And then the actual performance impact you can see here. So for GPTQ and AWQ, you get approximately linear speed up. It starts attenuating as you get to higher and higher GPU levels where the overhead starts to dominate compared to the speed up you get from parallelizing the data and the compression. But there are some things like, for example, the compression and the like Mo calibration context, some kind of things in the weeds of LLM compressor. We've started working on parallelizing those too. But as you can see, you go from like 264 or 750 in MetaLlama 3 GPTQ, the topmost row. And then with 2 GPUs, you approximately cut in half. And then when you go to 4, I think it's approximately cut into a third. But yeah, this trend kind of stays for all these different ones. And an additional change we noticed when we were doing the GPTQ DDP implementation, the accuracy was improving when we applied DDP. And this allowed us to actually find a small inaccuracy in the initial GPTQ implementation that we corrected and actually improved the accuracy for GPTQ across a number of models that we tested. So we're getting like a 1 to 5% error improvement just from for free after we made a couple changes to apply the same type of accumulation that we do naturally with DDP. So yeah, and then that's basically what I had. And I think that's kind of a brief rundown of the changes we made in version 1.0. Adding all this kind of offloading support was a pretty big pull, and definitely we're looking into going back to some of the more normal things that we've been doing in version 11. So yeah, we're looking at more MXFP4 support. We had a community member contribute this iMatrix observer, which is adding or yielding some pretty interesting results. You can go and join and look at follow the roadmap if you want. We have an RFC in our repository. There's a link down at the bottom. And if any of you use LLM Compressor and want to give feedback or have pain points, definitely take the survey and let us know what problems or awesome things you've done with it. So yeah, I'll stay here for a moment. And otherwise, yeah, this is, we've had going along with iMatrix Observer and the actual initial DDP implementation for AutoRound, as well as the data pipeline. We got a lot of help from community members, including like Intel, who developed AutoRound. So if any of you are interested in getting involved in any of this, please reach out, and we'd love to have you. All right, I'm going to go to the next slide. So I think it's this one is just saying, give us feedback and feel free to join us on the.
I think we could stay here for thanks a lot. That was a great overview. Good questions in the chat as well. Maybe this is a question I actually don't know myself from Ryan of like, why do we need to combine the activation errors from all GPUs before deciding how to quantize each module in AWQ?
So the theory behind AWQ basically says that the way that you determine how you're going to scale all of your weights in AWQ is dependent on the magnitude of the activations. And so we're basically just calculating the average activation values, and then we need to accumulate that. So if one of the so that when we go and we actually try and calculate the error, we need to know what scale values we need to test so that we can then add it together at the end. Like if module 1 was testing 1, 3, and 5, and module 2 was testing a ratio of 1, 6, and 7, you wouldn't be able to add them together. So that's the reason why.
Yeah, right. Okay. Let me go through some of the other questions. Yeah, if anyone has questions, feel free to raise your hand or come off mute. As well. I mean, one of the maybe like high-level questions, like, are there any improvements left for offloading or like memory efficiency? Or does these leave things in a pretty good place? Most of the things to achieve.
Yeah, I mean, in terms of you want to take this, Charles?
I was going to say, I mean, I think Kyle outlined the pretty important piece that's still missing with the GPU offloaded, like FSDP kind of implementation. I think this will likely unlock further improvement where we don't have to do any offloading off device at all, while being able to fit more onto onto multiple GPUs than like just having the entire model on a single GPU. That's something that we can't currently do. If your model fit on 8 GPUs, you couldn't use this to basically not offload at all. So when that's unlocked, I think that will open up like more than linear speed up. Like if you are doing, like, it's an entire different paradigm where we avoid CPU or disk offloading entirely.
Yeah, I mean, I'll add to, there's still a lot of work associated with the overlapping of data movement between offloads and onloads, right? So we have some support for this in terms of like trying to overlap the onloading of calibration samples while they're running. But there's still a lot of places where we can, leverage more overlap as the data moves and is processed. So definitely there's still a lot of work there, but this is like the core implementation, and this is like what is unlocking like the linear speedups that we're seeing today.
Yeah, okay, makes a lot of sense. Ryan, since you raised your hand and maybe related to AWQ.
I was just curious if there were any benchmarking that's been done on the speed up for the general compression. Any like results? Yeah.
So I'm not sure what you mean by the general compression. I think it's going to depend on what specific algorithm you're using, and by and large, I think we've gotten the major pieces of overhead like parallelized at this point, so it's approximately linear. But yeah, can you clarify what you mean about like the general compression?
Just generally, since you're building on like AWQ, which is like an existing algorithm, and you're sort of modifying it to work on vLLM. So I was wondering, since we're not using AWQ natively, how your changes on the library have improved the speed up of the compression. Does that make sense?
Yeah, so we are using it natively. We have our own implementation of AWQ. These aren't really running on vLLM. This is a separate library that you apply quantization to a model, and then you run that final model on vLLM. The model is going to run at the same speed depending on the quantization format. So none of that is going to change. The only change is how quickly you can apply quantization. And yeah, AWQ is one that like we had a ton of issues with, because you basically have to take your whole data set, try to quantize, check the error, try to quantize again, check the error. It's very slow. And so the data parallel aspect parallelize it as pretty much as efficiently as you can do. And at that point, we just have a bunch of overhead left from onloading and offloading, as well as a couple small remaining things.
Okay.
So yeah, I mean, that's basically what we like this table is looking at. Like, yeah, you go from something like these are relatively small models, but if you look at the Qwen 3 30B for AWQ, it took like multiple hours, and so I don't know, 450 divided by 60 is over 6 hours, and then we got it down to around 2 hours. So yeah, you see significant speed ups, and 30B is not the biggest model either. So when you're doing things that run for 24 hours and then it makes it run in 4 hours, that's a huge difference.
Okay. Yeah, very impressive.
And Andy asked, do we see speed up in the grid search? It seems like the whole algorithm sped up a lot. Do we see specific speed up in the grid search? And yeah, I think like initially when we were looking at AWQ, there was a thought that we might have certain grid points looked at by each rank. I guess I can go back to AWQ. In this case, I don't actually show the different ranks. You just have a single MSE value, but you're basically trying to quantize it slightly differently and then calculating the error. But we found it just makes way more sense to do all the ranks, but then only for half the data, since you already have all the data. And so the grid search is sped up, exactly proportional to 1 over the number of GPUs you have. So if you have 4 GPUs, yeah, you only have to do 1/4 of the data compared to not doing DDP.
Yeah, I think he also had his hand up. Yeah, Andy, if you want to unmute.
Yeah, can you hear me?
Yeah.
Awesome. Can you walk me through how you tested accuracy with DDP, right? Because I know, Kyle, we've talked before that a lot of you at Red Hat prefer GPTQ. I prefer AWQ. So I'm just wondering, like, when you added DDP, did you compare evals of like a model quanta with GPTQ, DDP versus non-DDP? And like, did you do evals? Did you do PPL, KLD? Like, walk me kind of through what you looked at before and after so that you made sure that DDP wasn't changing accuracy in a negative way.
Yeah, I think that's, so I did both GPTQ and AWQ, and basically for GPTQ, what we found very quickly was with minor testing, DDP was improving the accuracy of the models. Essentially, the way the Hessian was accumulated in the base implementation, and this is like every single implementation I see going back to the initial work of the paper, is incurring a ton of floating point error. And so by having that accumulation step where you get the like floating point error in each rank, and then you do a different way of accumulating, we were avoiding a bunch of that. So we re-implemented how GPTQ does this accumulation. We improved the accuracy, and we were doing GSM-8K on a sequence of like 2 or 3 models. And I also did some perplexity analysis. It was like very clear that we were beyond like not hurting things, making things much better. For AWQ, we had a weird, it's been weird, and we're still actually, if you go into LLM Compressor, you can see an issue open about like AWQ regression, because one of our CI tests got worse after we added DDP. So we fixed a similar issue in AWQ where the accumulation of the the activations was slightly off, like accumulating floating point error. And the GSM-8K evaluation got worse across like 3 or 4 models and 3 or 4 formats, but then the perplexity got better. And I've been trying to track down why this is happening. It's really a bizarre, like you would expect these to be largely correlated. You wouldn't expect to see for like 80% of your tests to show, you know, and one eval to be worse and another eval to be better, unless you're like specifically calibrating on this set, which we're not. So I think it has to do with difference between Hugging Face evaluation and vLLM evaluation, because I ran in a different way and I got differing results. But as of now, I'm doing a combination of like Llama 3, Quen 30B, a mixtral model, a vision language model, and an MOE, and that I'm doing GSM-8K Platinum, Wikitext Perplexity, and MMLU. So that's what I've been doing to try and figure out, like, make sure that AWQ is bulletproof after these changes.
Sounds good. Thanks.
Yeah, very cool. Appreciate the detail diving into it. Yeah, are there any other questions or points of discussion people have? So there's obviously a lot of work going on in LLM Compressor. So also, if people are interested, I'm sure there's a lot of stuff to help out with. Yeah, maybe that'd be a good point kind of on the last slide you have of like what of the future items you think would be most interesting to get help with.
Yeah, I think that we are trying. So there's some larger ticket items like this lifecycle refactor is something that I'm working on, but a lot of the questions regarding like all these different quantization formats and the integration with vLLM, and I think it's Hummingbird. I think there's a bunch of work that needs to be done there that could be parallel process between a number of individuals. Yeah, if you go and look at the issues that we have in LLM Compressor, you can see what things we're looking for help in. Usually we have a variety of things open at any given time. So yeah, if any of this seems interesting, like we need to get the MBFP4 micro rotations plugged in to vLLM. I think we have, like, I think it exists. It's just not hooked up to compressed tensor. Like there's a lot of integrations between like LLM Compressor and vLLM that I think need work for this next push. And yeah, if you're interested in getting experience in how these various disparate systems integrate with one another, I think that'd be an interesting starting place.
Hey, there's a question on YouTube Live, Kyle and Charles, and the question is, what are some tips and tricks you can share for picking calibration data for a specific use case?
Yeah, I can take that. So calibration data, typically, like you don't have the same intuition as you might have with like fine tuning a model, for example. Calibration data, like typically the algorithms implemented in LLM Compressor are much more generalized than the like fine tuning of a model. So the data set itself, like, almost doesn't matter. Like we typically use like kind of standard like ultra chat, you know, general like language tokens. In theory, like you can see some benefits of trying out different calibration data sets. So like, for example, if you're using like coding model and you calibrate using like coding samples, you could see better accuracy recovery from there. But you know, typically any kind of like language model chat data set is totally great to use for calibration.
Yeah, well said. I stand by that myself. Yeah, any last questions or things people have? Well, I think we can probably, or Charles?
I wanted to say, so Andy mentioned that he's been staying with, or someone was mentioning they prefer AWQ to GPDQ. And then I think Andy was mentioning that he's stayed away from GPTQ. And one thing I want to point out is that so in LLM Compressor, we have this different abstractions, transforms and modifiers. And so transforms like AWQ and smooth quant, spin quant, quip, these don't actually apply quantization. They like make the model easier to quantize. Then you have things like GPTQ, auto round, round to nearest. These actually apply quantization. So in theory, you'd be able to apply AWQ plus GPTQ. And in fact, most of the time, I think that tends to work better than either individually. So we're still trying to like make all these compose really nicely and improve the UX. But yeah, for your own mental models, those are separate things, and you can get better results if you combine multiple techniques at the same time.
Yeah, interesting point. Okay, well, yeah, we can leave it there for now, and yeah, appreciate everyone who's came here and showed your interest. As always, we want to thank you for being a part of the vLLM community, including LLM Compressor and everything else that's a part of the ecosystem. Let us know what talks or things you're interested in the future. Of course, join us on the vLLM developer Slack, slack.vlm.ai. There's an LLM Compressor channel there where you can talk directly to the core devs like Kyle and Charles. And we have a SIG quantization channel as well, where we regularly talk about quantization, both in vLLM, LLM Compressor, and other integrations. Yeah, we're hiring at Red Hat if you want to work on open source. We very much are growing the team, and yeah, excited to have.
What are you hiring for, Michael?
People join us. We're hiring all over for working on vLLM on the sort of runtime team, for working on LLM Compressor and speculators, for training new model compression or model acceleration methods, on the ML research team for coming up with new methods and doing evals and research on how to apply them more effectively, on LLMD and distributed Kubernetes scale sort of deployments of vLLM and the very large cluster scale inference infrastructure for deployed engineers for getting these things or these deployments scaled up into enterprises. Yeah, just let us know, and we probably have a place for you. So
yeah, AI developer advocate as well. So
yeah,
if you're interested or you know somebody, find Michael or I in Slack and just send us a quick message.
Yeah, well said. Well, yeah, hope everyone has a good week, and yeah, I think we'll actually catch you in 2 weeks on April 30th. So yeah, have a good one. Take care.
Bye, guys.